pretty cool.
It was fun. But you can do it with your, I mean, I think your renewable plants do this. And maybe consider.
I think for our modeling, I think anywhere where we have a REPCA model, we would use its parameters for now and put that in the power flow.
Mm-hmm. All right. Next topic. This is going to look similar, but let me emphasize it is actually a completely different topic. Except the curves are going to look similar and it's confusing. So this is what I call voltage set point tolerance. All right. So where I started with, Tom was asking, do your cases tend to operate near their megabar limits? And if you haven't looked, the answer is yes. A huge percentage of the generators in WEC are at a limit in a power flow case. And I was motivated, do I have this in here? Yes. I was motivated to start looking at this in 2017 because Sean Patterson at the Bureau of Reclamation, he was giving a presentation actually about exciter models and including over and under excitation limiters, because all the new IEEE standards are calling for that. But one of the first slides Sean put up was, before you do any of this, go fix your power flow cases because their bar outputs are all junk. That was like, and I was like, no, they're not. And then I went home and I looked and I was like, oh my gosh, they're all a lot of them are at their limits. And the reason it matters is because if you start modeling over and under excitation limiters, and your initial condition is almost at the limit, you're going to be hitting these over and excitation limiters as soon as you start including them in transients. You've never done that because you weren't modeling them, so you didn't really notice. So the power flow is going to be an issue. So then I was like, well, I could just tell you guys to go fix your set points on voltages so they're not fighting each other, but you've got like 2,000 generators to tweak. So that got me thinking some more. Yeah. Yeah. And when I looked at East and West and ERCOT cases, it's very typical for 1/8 to 1/4 of all the generators in a power flow case to be at a limit. About half of them of those at the max and half at the min. So I think I went.
How many of your generators would be operating at their limit in normal operation? Like I'm thinking 0, right?
0 is what I was told. Yeah, Sean was like, we never do that. But not very many of them. 0 is what I was told. Yeah, Sean was like, we never do that. But not very many of them. But it's not 1/4 of them. And okay, and you wouldn't have units that were, say, 50 miles apart where one of them's at the max and one's at the min. Because that's what's going on here.
But you just said you have units consuming bars, right?
Yes.
But not at their min limit. Okay, so they would be at their min limit but not at their max limit. How many are at their max limit?
Running post-contingency.
No.
No, I mean
normal
just
operation.
Normal operation.
Nobody's going to sit there and operate at their max limit, right? That's
Yes.
just.
Well, you're looking at a case that's a heavy case.
No, I looked at light spring, light wind. It doesn't matter. And
Operate at their max limit, right? That's
Yes.
just.
Well, you're looking at a case that's a heavy case.
no, I looked at light spring, light wind. It doesn't matter. And it's not a. It's all that you've got generators near each other whose voltage set points aren't quite coordinated. One of them's 1.02, one of them's 1.03.
I think sometimes in our base cases, if you look at a base case, you'll see that a generator is outputting its max megawatt as well, and that impacts the OEL, UEL. So like if you go in and you take a base case and you just do simple gen tuning, you can back off of those limits. But it just takes a quick gen to the base case.
Yeah, so let me just go jump ahead. This was, and this is only one WEC case, but I looked at like 10 and they were all the same. It's like, so if this is a plot of, if they're at 100, this is the number, the percentage of generators at their max limit, and this is the percentage at their limit. And in a wet case, 6 or 7% on each end, so 13% overall. We're at a limit. This was, in a second, I'm going to talk about how to add in a tolerance to the voltage set point in the power flow and let it kind of move things around. And this was after I did that. And basically, generally what's happening is it's, coming back more towards flat, where things aren't at limits as much. So units down here are tending to go up, units over here are tending to go down. I'm going to explain why that happens in just a second. So just so that you can feel okay though, I did go look at an Eastern Interconnect case, and in their case, 25% of the units were at limits in the base case. The bigger the case, the harder it is to manage the input data, so this is not surprising. And ERCOT was about, 15% were at max and 4.5% were at min. So let's go talk about how to fix this. All right, first of all, what do we do right now? I've kind of flipped this on the edge, and we're looking at Q going this way and voltage going this way. The way generators work now is we give it a set point, and Q varies between the min and the max until it hits the min, and then it goes vertical. The Q is constant at the max or vertical at the min. So that's how we have done power flows since 1960 something. And it hasn't changed. That's how it's always been. All right, so what do generators actually do? So I went to a NERC meeting. Sometimes generator people show up. There were like 5 or 6 of them in the room. And the question was posed to them, when you're given a voltage, do you operate to exactly that voltage? And at first they were like, yes. And I was like, well, what if you were off by 1%? Oh, that's close enough. 1%, that, to a lay engineer, that's like, oh, that's pretty close. But to us, that's like 0.001. That's a big voltage difference in our power flow world. So the fact is, and what I was hearing from them, 2% is not unusual. If you tell me to be at 1.04, I'm like, okay, somewhere between 1.02, 1.06, I'm good. That might be a little wide, but that's what the generators actually do with the information given to them. So that is beneficial to consider. So essentially what the generator is being told here, and they were like, well, it depends who's working that day. Right? Some guys are more attentive, trying to stay in the middle of the box, and some guys don't care that much. So essentially what I'm proposing to put in a power flow is to kind of model this human behavior of staying in the yellow box, with the side effect that it's going to fix the problem we had of generators always being at limits so much.
So we actually allow them a band
Yeah.
to target, so
1% about right, or
it depends on the,
half, but no less than 0.5% probably.
no, yeah, no, it could be more.
Maybe,
Yeah.
depends on the generator. Okay, but the point is you give
Closer than that? Some are tighter than 0.5%?
Oh, yeah, we give them, less than half.
Okay. Okay, so it depends on, but is that every generator or just some particular important ones?
Particular one.
Okay, but the point is you give
Closer
them.
than that? Some are tighter than 0.5%?
Oh, yeah, we give them, less than half.
Okay. Okay, so it depends on, but is that every generator or just some particular important
Particular
ones?
ones.
Yeah. So in simulator, what I'm going to allow now in version 21 is there's a voltage tolerance with each generator. So you can set them, if they're 0, which they are by default, we just do what we've always done. But if you give them a tolerance, and the control at your generators with the tight bands, it's not automatic. It's still got a person moving the exciter up and down. Or is there a closed loop control making that
I
happen?
thought it was through the AVR.
Well, the AVR has a set point though, and as system conditions change, it needs to go up or down if it wants the voltage to stay fixed. the question, is there feedback there? Okay. Fine to ask them. Most generator folks I ask are like, no, it's the operator hitting the mouse to go up or down. The hydro plants, there's not an operator there, though, right? There is one, okay. Your plants are big enough, they have, yeah. So anyway, what Simulator has added, there's a new field in version 21 on a generator. Just all right, there's a new field on a generator called the voltage set point tolerance. When I come into generators, there's actually another new kind of default case info display here under generators that has all the common columns for voltage control. Basically got added while I was adding this code because I needed to be looking at this all the time. But there's a set point, which you've always had, and then there's a set volt tolerance. So if I hover over this, does it give me a good hint? Tolerance of the desired per unit voltage set point at the regulated bus. So what this is going to do is, instead of treating the equation when I'm meeting the voltage set point, instead of being voltage equals set point, it's going to follow a curve so that at the minimum VAR output, the generator will be at its which way am I going? Yeah. As the voltage goes up, the generator will go to its minimum VAR output, and as the voltage goes down, the generator will go to its maximum VAR output. So instead of the equation you learned back in school where you have a PV bus, we're at a power and a voltage equation, we now have follow this yellow or green line, which is not that much harder. In the code, it's a lot of extra lines of code, but numerically, it's not that much harder. and the Q here, it's different than the droop curve I was just talking about before, because the Q on those curves, with the Q arriving at the regulated bus, this is not that. This is the Q summed up out of the generators. So all the generators doing this control together. And so the equation becomes, instead of voltage reg minus the set point equals 0, it's just the equation of a line where we have voltage reg minus the set point plus the tolerance. Just work it out, but this is the exact equation that we use. And the red variables are functions of the terminal voltage. So it does make the Jacobian a lot more complicated, but it actually is nice because if I have two generators near each other, one's operating at max, one's at min, and I give this little tolerance, they're just going to kind of figure out where to go so they're not both stuck at limits. So in the software, all that's added for this is just one extra parameter on the generator. If it's 0, or actually I think it's anything smaller than 10 to the minus 3, we just go, that's a set point. We'll ignore that.
I have one comment, Jamie. I actually just utilized that last week and put all the voltage schedule into an ops file with that tolerance. Some of our bands, though, are not equal, so you could have like a plus 4, a minus 2.
Correct. You're going to have to mess with the set point to put it in the middle.
Yeah.
I debated, but it's like 2 input parameters then. Yeah, so what he's saying is he's got these set here. So some of their bands are, this might be plus 0.005, and the down might be 0.001. So in order for him to use this tool, he needs to change his set point to be in the middle of that and use a dead band of 0.003. So you would have to do that.
That wouldn't be hard to implement.
It would be easy to add that, but he's the first customer I've learned to actually use the feature. So.
I'll send you the ops file.
And in the short run,
Did you find it useful?
Did it move? Yeah.
I was worried that it was gonna fail the case.
You know,
with the-
I've played with, say, a dozen cases. What I find is it's more stable. Most of the power flow failures are you're fighting, trying to figure out which generators are at limits, and that's what's causing the problem, and this is making that better.
I haven't had a chance to utilize it. I literally
Yeah.
finished it last Friday.
Correct. Yeah, so, if I come in here and hit solve, have a good drive back, guys. Yep.
Bye.
You can just come in here and I can set the top, this is a wet case. If I come in here and I set present as base case to kind of keep track of where everything is right now, use the difference case tool. And then I set the tolerance at every single bus to say 1%, 0.01. Say yes. I'm breaking my rule of you should try this before you present, but I think it'll be all right. But yeah, it's solved real quick. And if I were to go, just look at that. All these units backed off their limits, mins and maxes. And they didn't start hitting limits then. I didn't see anything hit a limit. They're all backing off. I think there's a field. All right, this megavar percent field. Let me filter by only generators that are closed. This is telling me where am I at within the plus 100 to minus 100. This is kind of hard to do actually. What I want to look at is compare the average of the negative values so the average negative value is minus 36% now. Let me compare that to base case. Shoot, it doesn't, I'm not positive. No, correct, that's not part of the difference case tool, so I can't do that. It's just showing me the base. But what you see happen, I have it in the plots here, I can kind of show. But what I saw happen on one wet case, no, correct, that's not part of the difference case tool, so I can't do that. It's just showing me the base. But what you see happen, I have it in the plots here, I can kind of show. But what I saw happen on one wet case I went through, I started out with 13% of my units at a min or a max, giving even just a 1% tolerance, about half of those went away. So, but what's happening is everything's trying to come back to the middle of its range. If I give a tolerance of 50%, which is ridiculous, it probably won't solve. But you're basically telling everybody, try to be in the middle of your range, is what's happening. And as I make that tolerance bigger and bigger, I went all the way up to 15%. It kind of, I suspect at somewhere around 3%, I fixed all the bad input data, and I'm really not getting much benefit as I go further, and I'm probably messing up and screwing up the case at this point. But in the short run, I feel like this maybe is a good thing to do, like James was doing, where he was just trying to come up with better set points. What you could do is run this, and then when you're all done, take the voltage at the regulated bus, copy that over to the set point, set the tolerance back to 0, so you can then go share it with other people, and they're still back where they were, but you kind of mucked around with your set points.
You'd have a better initial state for the transient.
You have better initial state for the transient. You'll have, I don't know this until hundreds of people start using it, but I think the power flows in general will be a little bit better, even post-contingency solutions. Yeah, so here, actually, this is a cool picture. So the blue value is where I started. So you can see it's kind of skewed where lots of units are at their maxes. Sorry, not this one, the blue one here. Higher numbers are at their min and max. And as I increase the tolerance, the generators just slowly start trying to move towards the middle of their range. Which, I mean, it's not shocking, that's what my equation is telling them to do. So it's not a surprise. Yeah, and the same happened here. This was a wet case, about half of them go away. About half of them go away in the east, giving just a 1% tolerance. And about half go away in ERCOT. And I went and grabbed an old peak reliability EMS case that Joe sent us long ago before he left peak. And my hunch was in real time, there wouldn't be any units at maxes. And lo and behold, there weren't. There are many, many fewer are at a max limit. And more than that, if I give them even just a little bit of tolerance, almost all of them go away. And that's because they have the constraint of reality on their side. That they're given, this is where it's operating right now. So, all right, so my initial test, like James said, I think most people were like me and thought, wow, this will be harder to solve. I'm worried it's going to make the numerical solution of the power flow harder. My gut feeling is it's not. It's going to make it easier because it basically gives the power flow an out. That if we're conflicting and I really can't get this voltage set point, it lets me move a little bit away from it. So, and this is a help link that kind of describes how all this is done. But what it means is, again, if I go look at the power flow solution, I have a whole bunch of weird new kinds of buses. There's a bus in here that says PV tall. There are literally, I have just changed it, there are no PV buses in this whole power flow. So, let me repeat that because it confuses. Usually when I give this presentation at a WEC or a NERC meeting, I get people coming up at the end that says, where did the PV buses go? I didn't see them. It's like, they're gone. You know, we have things that say voltage equals set point. We no longer have that. We have voltage. Did I show that equation? Yeah. I just want to reiterate that. This equation instead. So you have to go take Tom's book and ignore the PV bus chapter. But it's the same concept. We're just swapping out this equation for this equation. It doesn't make things more complicated because honestly at this bus there's a power equation already that's kind of complicated. So it doesn't hurt to add a Q equation with it. These voltage equations were always kind of weird, just stuck in there anyway. All right, I thought we could end a little early on the last day.